So my name is Ben-weiss. I'm a professor in planetary science in EAPS, and I'm interested in meteoritics, planetary geophysics and history, and in particular paleomagnetism and the history of magnetic fields on planetary bodies. So probably the most important event in my life that led to my interest in planetary science is when I was a high school student. I went to a summer camp in California where we observed asteroids over the summer. And that summer we had a visit from a researcher at the Space Telescope Science Institute, the institute that was managing the recently launched Hubble Space Telescope. And he told us about a program whereby amateurs, and only amateurs, if you had a degree in astronomy or planetary science, you were not allowed to apply to use the Hubble Space Telescope for a research project. It was about 5% of the time of the director guaranteed for amateur astronomers in the world. So a bunch of us at the program got together and decided to look for moons around asteroids. And we applied to use the Hubble Space Telescope, and we were guaranteed we won several hours of time on the Space Telescope. And that was one of the most exciting events in my life, to go down there and actually look at photographs taken with this telescope in the sky. And ever since, astronomy and planetary science have been my passion. Well, I grew up in upstate New York, and I was kind of a classic, typical suburban kid. And I went to college in Massachusetts, and then after spending a few years in Singapore, decided that I was really fired up about going for the broke in planetary science, becoming a professional. So I went to Caltech for grad school in planetary science, and this job happened to open up. I always thought of EAPS as one of the best places to be in the world, and I was lucky enough to be on the job market just when the job opened. So I'm interested in planetary structure and evolution, from the formation of the solar system to the formation and evolution of the building blocks of the planets, planetesimals and asteroids, to the bodies themselves that form from these objects, the planets, Mars, the Moon, and the Earth, and other bodies. And in particular, I study samples of these bodies. So that's meteorites that were naturally transferred from Mars or from asteroids being blasted off the surface, and return samples, Apollo samples, and recent samples returned from other bodies. So we look at these samples and try to identify records of planetary history and geophysical processes in them. And in particular, one of our interests is to look for the remnant magnetization and what it can tell us about the history of planetary magnetic fields, and also the thermal history of the bodies and their climatic evolution. So I don't actually have a schedule that I could tell someone that's a typical schedule, because every day is different. Usually it involves spending too much time in front of my computer, going to the lab and maybe making some measurements, and talking to students and researchers in my group. And as well, of course, as teaching and activities associated with education. So, I don't have a regular schedule. Actually, that's one of the things I like most about my job. The main way that we investigate the history of planets is through their samples. So we have in our lab Apollo samples, meteorites from asteroids in Mars, and we study in particular the remnant magnetization and geochronology of these samples, as well as their petrology. So basically, these rocks, which formed up to many billions of years ago on other planetary bodies, record in their formation conditions, as well as their subsequent alteration, the history of these bodies, the timing and intensity of ancient magnetic fields, volcanic and magmatic processes, as well as even climatic processes. On the 7th floor of the Green Building, we have a Paleomagnetism laboratory. And the focus of this laboratory is to measure the remnant magnetization and rock magnetic properties of planetary materials. So we have magnetometers, which detect their magnetic field and can remagnetize them. And we can observe how they respond to these applied laboratory magnetic fields to understand something about their interior structure and mineralogy. So these magnetometers come in a lot of different varieties. Maybe one of the most interesting one is full of liquid helium. So it's got sensors that are at minus 269 degrees Celsius and are superconducting. So it's a very, very sensitive type of magnetometer. It allows us to detect the remnant magnetization of extremely weak samples. So these samples wouldn't stick to your refrigerator, but they nevertheless record in them magnetization records of ancient magnetic fields billions of years ago in other planetary bodies. So we do lots of different things in the laboratory. Just to talk about one of them that's been of recent interest, we've been investigating the moon. In particular, we want to understand in a broad way to what extent is the moon like a planet rather than, say, a small body. So by that I mean, to what extent is the moon differentiated? Does it have an internal radially layered structure that's compositionally varied, that reflects processes on the body, magmatic and geophysical, subsequent to its formation? To what extent is the moon an evolved object with an extended history? This is one of the biggest questions in lunar science. It goes back to before the Apollo missions, when there was this great debate as to whether the moon was a primordial pile of unmelted space dust, or whether the moon was like a body like the Earth, with volcanism and a metallic core and a mantle. And in particular, what we're interested in is, did the moon form a metallic core? And did that core generate an ancient magnetic field the way the Earth does today? That is, by motion of metallic liquid in its interior. And the moon today certainly does not have a magnetic field, but Apollo samples returned in the 60s, late 60s and early 70s, show evidence of remnant magnetization, that there was a magnetic field possibly present when they formed. So what we've been doing is analyzing these rocks to try to determine the origin of this magnetic field and its timing. And what we've found is that the moon did indeed appear to have a global magnetic field like the Earth did, extending from at least 4.2 billion years ago to 3.6 billion years ago. A challenging aspect of this is that although rocks will record magnetic fields when they form, when you're talking about planetary samples that are billions of years old, so moon rocks that are older than 3 billion years, asteroid samples which are 4.5 billion years, these samples are older than the vast majority of rocks on the Earth. And they've lived through a crazy history of impacts, thermal metamorphism, and all kinds of maybe even Mars aqueous alteration, weathering. So these things have lived through billions of years of solar system history, and it's not easy for them to retain records of the earliest period of their formation, given all the subsequent events that they've been subjected to. So what we need to understand when we look at the record in these rocks is to what extent does it reflect their early history rather than much later deformational or thermal events. So basically, we would like to peer back through all of this subsequent history that's affected these rocks and learn something about their time of origin. And that's probably the most challenging aspect of making these measurements. Working on Apollo samples and meteorites. So Apollo's samples are return samples by, of course, the Apollo missions. And the meteorites were naturally transferred from bodies following impacts on those bodies. And then these things wandered around the solar system until they accidentally landed on the Earth. Well, what's kind of exciting is that the next decade to 2 decades, particularly the next decade, promises a diversity of returned samples from other bodies. So deliberate spacecraft missions to go to bodies and return them. So we just had samples returned from a cometary tail and from an asteroid, and also the solar wind, and there are a number of missions being planned to return samples from other asteroids, from Mars, and maybe even from cometary nuclei. So there is tremendous amount of work that can be done on deliberately chosen samples from weird and interesting planetary bodies.